Welcome back. So this will be the final new content video in Unit 2, and as you can see today we're going to look at IP version 6 and also DNS, or the domain name system. So a quick overview, we're going to look at the IP version 6 formats and also motives, so why it was created. Right, then we'll look at DNS, the domain name system, how it works. And we'll also look in a bit more detail, so something called DNS caching, basically saving the result of a DNS query, and also DNS hijacking, right, so a form of farming. Right, so if we look at IP version 6, now if we recap, there were 3 ways we mentioned to alleviate the IP version 4 shortage. Right, so pause the video and yeah, hopefully you can remember some of these. So the first one was subnetting, and the way subnetting works is, well, rather than just having the kind of fixed, cutoff between the network ID and the host ID, and well, therefore having, kind of large amounts of unused hosts, right, instead with subnets, well, then we can basically specify exactly where we're going to split the network ID and host ID. So if we only need, let's say, 1,000 hosts, well, then we would probably want to have, let's say, 22 bits for the network ID, right, while leaving 10 bits for the host ID, because 2 to the power of 10 is 1024. Therefore that's going to be enough, right, to accommodate 1,000 hosts. Right, then we also looked at private IPs. So rather than every user device having to have a globally unique public IP, instead we can say the router can have the public IP. The globally unique public IP, right? Whereas the end devices, well, they can have a private IP that's just unique for that for that network. And if they have to communicate with a device on another network, well, then they're going to go via the router, and the router is going to use NAT, right, network address translation. It's going to store network address translation forwarding table, basically just kind of mapping the private IP and port number, that the packets are sent from, to the router's public IP and port number, right, that it sends the packets out of. Right, then when it receives that, well, then it's just going to convert between them. Therefore it can send it back to the correct device. Right, and finally then, just dynamic IPs. So rather than the device having a permanent IP that it's using, even if it's not even turned on, well, a dynamic IP what they're going to be given a lease, and that can be 1 hour, 4 hours, 8 hours, maybe 1 week, 1 month. But if it's not renewed in that time, well, then the IP will become available, right, for someone else or for a different device to use. Alright, so while these 3 methods are good, then I guess instead of actually using this, well, we could have just come up with a completely new IP protocol, which is going to support more addresses, and that's basically what IPv6 is. So rather than trying to use these kind of workarounds to combat this IP version 4 shortage, well, let's just create a completely new protocol. And the thing is, while these do work, in reality, like, obviously, while there's more and more people, there's more and more devices. So these 3 are not really a permanent solution, whereas IP version 6, well, that's more of a permanent solution. As we'll see in a minute. So IP version 6, well, uses 128 bits, right? That's 2 to the power 128 different different IP addresses, and I think if I remember, that's about 10 to the power of 38. So that's like a gigantic number. If you think like that means basically every single person can have, I don't know, probably 10 to the 31 different IP addresses, or I don't know, maybe like 10 to the 30 different IP addresses. So effectively, we're So with IP version 6, well, we're never going to run out, basically. Right, then the actual format, so it's going to be written as 8 groups of 4 hexadecimal digits, right, and each group is separated by a colon. So for example, I guess here, and of course, the colon, right, just to separate them. Right, however, this can also be shortened, or I guess sort of compressed. Right, so leading zeros. Now, when it says leading zero, for example, anything starting with a 0, and also groups of all zeros can be omitted. So, for example, here, these groups of zeros. Now, this, So this second, groups of all zeros, there are actually some caveats to that, which we'll see in a minute. Right, so for example here then, all of these in red, they can all be, omitted, deleted, because, this one here is a leading 0, obviously, 3 leading zeros. Right, here we have a consecutive group of all zeros. So if we see, this can actually get shortened down. So when we see, So when we see consecutive groups of all zeros, then we can replace one instance of those, with, just a double colon, effectively just, leaving out those zeros. Yeah, okay, alright, okay. So the thing to note, well, we can only do that for one group of all zeros. Now, if we have two groups of all zeros, okay, we can't omit both of them. Yeah, well, right, yeah, okay. So I guess, well, two, non-contiguous groups of zeros. Right, and that one we'll see in a minute. Okay, so it seems the animation is a bit messed up. Right, it says the transition from IP version 4 to version 6 has been going on for many years. I think like at least sort of 10, maybe 15 years. Yeah, however, even now, most devices still use IP version 4. Right, so I guess because of that, well, to allow interoperability, or I guess, yeah, backwards compatibility, then we also have something called a dual IP version 6 and IP version 4 address. And basically that's going to be an IP version 6 address, right, just with an IP version 4 address kind of stuck on the end. So the reason for this is, well, if a receiving device only supports IP, yeah, right, well, yeah, okay, right, okay, so if a receiving device does support IP version 6, well, then it can use, the IP version 6 portion. While if it's, some old hardware that only supports IP version 4, well, then it can still use that, right? It's not going to get confused. Yeah, it's not going to, sort of not know what to do with this new IP version 6 address. Alright, so in this dual format, well, 6 groups, and if we think, well, 6 groups of 4 hexadecimal digits, well, 1 hexadecimal character is going to be, what, 4 bits. Therefore, well, yeah, 4 hexadecimal characters is going to be, well, 16 bits. So if we have, well, 6 groups of 4, right, that's going to be 96 bits. Yeah, so 96 bits are allocated for the IP version 6 portion, right, while 32 bits are for IP version 4, and that's going to make it 128 bits total. So if we look at an example, well, if we see, yeah, obviously here, well, this orange, yeah, this orange is, well, the IP version 6 part. Well, this, yeah, right, okay, yeah, so this blue, well, this is the IP version 4 part. And notice how they're actually written in the same format. Like, for example, the IP version 6 is going to use the colon, right, whereas the IP version 4, well, that's still going to use the, yeah, well, the dot, right, the full stop, just to distinguish which is which. Alright, and then I guess, well, here's just another example. So here we're saying what the middle two groups of the IP version 6 are all zeros. So I guess what that's going to be here, that's well, obviously, yeah, group 1, group 2. Right, so what, well, group 3 and 4. Yeah, group 3 and 4 are then going to be all zeros. Okay, so let's think then, why can we only have one group of all zeros? And I'll say pause the video, right, have a think about that. So if we have the IP address, well, let's say this. Now, if we see here, well, this is going to be invalid, right, because we actually have, well, 2 groups of zeros. Now, if we think about this, we're not going to know how many zeros are going to be in this first group, and obviously, yeah, how many zeros are in this second group. So, for example, well, yeah, right, okay, so here we see 4 out of the 8 groups, right, hence we know there's going to be, well, 4 groups of all zeros, right, in order to make the 8 groups. But how do we know if there's 3 groups of zeros between, say, B and C, right, and then, yeah, only 1 group of zeros here? Yeah, or there could be, well, I guess, yeah, 2 groups of zeros here, 2 groups of zeros here. Yeah, or there could be, well, 1 group of 0 here, 3 groups of zeros here. So if we have kind of 2 gaps like that, well, then it's just going to be ambiguous. Yeah, so hopefully that makes sense. Right, whereas in contrast, if we have, let's say, 1 group of zeros and then 3 groups of zeros, well, then we can write that as follows, where I guess this one, hang on, right, I guess this one, well, since here we only have 1 group of zeros, then I guess we can keep that. And the one here where we have 3 groups of zeros, well, since this is, well, the longer one, right, then we may as well just, sort of, yeah, I guess kind of like eliminate that, right, yeah, remove that one, yeah, just to save space. Right, so then let's just look at what the different IP version 6 groups mean. So the first group is going to be the network ID, right, that's the first 3 hex groups, or the first 48 bits. Right, and, well, yeah, okay. So similar to an IP version 4 address, well, there's going to be a network ID and a host ID. Right, then, well, the fourth hex group is going to be the subnet mask, right, the 49th through 64th bits. And if we think an IP version 4 address, now there you're going to have, well, yeah, right, okay. So there you're going to have, what, a 32-bit IP version 4 address, right, then you're going to have a 32-bit subnet mask. So in that case, well, yeah, right, okay, yeah, okay. So the IP version 4 address and subnet mask, well, they're going to be 2 distinct things, right, 2 separate things. Whereas IP version 6, well, the subnet mask is actually built into the IP address. Alright, then finally, well, just the device ID, host ID, right, that's the last 4 hex group of numbers, right, so the last 64 bits. Yeah, so if you think about that, well, obviously we had a problem with IPv4, right? Not enough. Now, if we think here, well, that's going to be what 2 to the power of 64, which is just like a gigantic number of different devices. Right, so for an example, well, then you can see what the first 3 groups of network ID, right? Then 1 group's the subnet mask, and finally the last 4 groups, right? The device ID. Okay, so actually for IP version 6, well, there's going to be more questions at the end, just asking, well, is this a valid IP address, right? Is it invalid? But yeah, I guess, well, currently then we'll just move on to DNS, or the, well, domain name system. Alright, so hopefully people know what a domain name is. Right, if you don't, well, basically it's just the website address, right? E.g., well, Baidu.com or YouTube.com, yeah, like abc.xyz, yeah, whatever that website is going to be. Right, so when you communicate with a server, e.g., while sending a web request, then the computer or network, right, doesn't actually use the domain name. Alright, so let's think, what does it use instead? So instead, well, all communication is going to be done via IP addresses. Right, hence there needs to be a way to convert a domain name, i.e. what you type in, let's say, well, google.com, right, youtube.com, right, into its corresponding IP address. And this is what DNS, or the domain name system, does. Now, often they'll actually ask, so they'll say, well, why do we use, domain names for humans? And basically you can say, well, yeah, okay, so remembering something like youtube.com, well, humans are good at remembering words. I mean, right? Yeah, okay. So humans are good at, well, remembering words. I guess, yeah, sort of remembering letters. Whereas generally, I mean, we're not really very good at remembering numbers. Like, a lot of people struggle to remember their phone number. Yeah, myself included. So trying to remember, thousands of different IP addresses, I mean, well, basically that's just going to be impossible. Alright, so let's see how well DNS works then. A client is going to send a DNS request asking to resolve a domain name to an IP. And I guess, well, when it says resolve, I guess, well, just convert, right? Convert a domain name to an IP. So if we see here, well, this is the client, right? Just our device. That's going to send a DNS request. Now, I mean, don't worry about these, well, type A, type, yeah, yeah, right, yeah, okay. So to be honest, I'm not sure what the different DNS types are. If you have a website, then yeah, I mean, well, probably you'll be familiar with this as well. There's just sort of, well, different types of DNS. All right. Anyway, so if we look here, well, I guess here they're requesting, well, what's the IP address of, well, mail.google.com, right? Yeah, this subdomain. Right, that's going to go to the DNS server. Well, the DNS server is going to, have a record of this. Right, then of course it's just going to send it back. So here it's saying, well, 1234. Right, that's the IP address, right, of this domain, or of this subdomain. Alright, so yeah, I think we saw that, right? Domain name, well, yeah, mail.google.com, right, returned IP, well, 1234. Alright, so that was actually a bit of a simplification. Like, in reality, DNS is hierarchical. So a DNS record is going to be looked for in the following places. And if it's not found, then it's going to be looked for kind of in the next layer. Of course, well, if it is found, well, then it can just, sort of resolve that. It can just return it, right? It's, yeah, okay. So, well, then, of course, it's finished. Right, so first then it's going to check the browser, because actually when you visit a website, I think usually a browser will store this DNS record. I think it's not very long, probably just 1 or 2 minutes. And the reason for that we'll see in a minute. Basically it's for security. Yeah, that's why it doesn't store it for longer. Right, the operating system, well, that can also have a list of DNS records. I think some of them might be built into the operating system. I don't know, yeah, maybe like Microsoft has some, sort of built-in DNS records. However, some of these can also be created by the user. So the user can also add custom DNS records. For example, let's say they're saying that, I don't know, yeah, like ABC, yeah, like .xyz. Let's say they would say, well, this has the IP address, I don't know, yeah, 2.3.4, yeah, .5. So yeah, okay. So it's also possible for the user to, well, add custom DNS records, which in some cases can be useful. Let's say if you've got a website and you want to test it, and yeah, you want to test it by accessing, just sort of like a real domain, right, rather than only accessing, let's say, I don't know, some, kind of, yeah, local host domain. Right, so that's when it can be useful. Yeah, I guess some other, sort of networking, yeah, more advanced network configuration issues. However, we'll also see in a minute, right, this can also be, I guess, abused, right, in order to create DNS hijacking, where what you can have is, well, let's say you have something like, I don't know, let's say, right, google.com, right, and then, yeah, okay, so basically you can set up a DNS record, let's say going to my server, right, instead of going to, the real google.com, right, then, of course, well, if it goes to my server instead, well, then I can have, a fake Google page, But the thing is, to the user, well, if they look in their URL bar, well, their URL bar is going to say google.com, right? Even though it's not actually gone to the the real Google server. So yeah, of course, right, that's going to be a security issue. All right. However, yeah, right. Okay. So if the DNS record is not known in the browser, right, and if it's not found in the operating system, well, then it's going to go to the router. The router is actually going to have a DNS server built in, and I guess yeah, we can say, well, that's the cache. Basically, just the kind of saved records from previous requests. Right. If the router doesn't know, well, then it's going to go to the ISP's DNS server. So what ISP, right, Internet Service Provider. Right, and if that doesn't know, well, then basically it's going to go to the global DNS servers. Now, the first one is going to be the root. Now, the root server doesn't actually know the DNS records for what. Right, okay. So let's say the root server doesn't actually know any DNS records. I mean, well, basically for anything. However, what it does know, well, it's going to know the So it's going to know the servers that handle the various TLDs, right, top level domains. So let's say if you have like a .com, well, .com is one top level domain. Let's say .org is going to be another. .edu, right, .education. Obviously many, right, .gov. So what is okay. So this is also going to be all of the country codes as well. So what the root server will do is, let's say if we go to google.com, well, then it's going to say, well, if you're looking for a .com domain, right, then this is the IP address of the server you need to ask. Maybe right 6.7.8.9. Whereas let's say if you're asking for a .org domain, well, maybe that's going to be like 1.1.1.5 or something. Okay. All right, and then okay. So when it goes to that, well, these can then sort of pass it on to the authoritative name server, and this is going to be the one that actually knows the DNS record, for these domains. All right, and yeah, I think that we'll see in a minute. So yeah, for example, let's assume you type in yahoo.com into your web browser. I think a lot of people probably don't even know what Yahoo is. I guess especially depends on which country you're from. Alright, so yeah, let's see how this DNS record would be resolved. And I guess, Yahoo is kind of like the old Google, right? So I think actually 20 years ago, Yahoo was actually the most, most visited web page, or sort of 25 years ago, right? Maybe in 2000. Right, so first then we go to the root server, and the root server, well, that's the top or the root of the DNS hierarchy. Right here it says there's 13 sets of these root servers that are strategically placed around the world. I think this sort of PowerPoint, this video that I took the screenshot from, this is probably quite old, right? So maybe there's more than 13 now. Now, actually, if people do want to see this video, because actually this channel has a lot of good videos, so I think the name, it's like PowerCert, right, CERT. So I think if you search like PowerCert animated videos, and yeah, that's going to be the name of the channel. Okay. So their channel is just all about networking. Alright, so here they say, well, they operate by 12 different organizations, and each set has their own unique IP address. So I guess that makes sense, well, because, right, okay. So since the root servers are in different places, well, therefore they're going to have a different IP address. And when it says strategically placed around the world, basically just in different locations to provide, low latency or fast access. So yeah, of course, there's going to be some in Europe, right? There's going to be some in America, right? Some in Africa, some in Asia, some in South America, right, etc. Alright, and I guess, here we just see, the browser and operating system, of course, as mentioned, okay, so these are going to store some, DNS records. Right, then when it says resolver, that's the ISP's DNS server, ISP's DNS server. Right, so then we go to the next stage, the TLD, top level domain server. Okay. So this, of course, is assuming that, we've not found it on the computer, or we've not found it in the ISP. Because, if we found it there, right, okay. So if we found it at one of those stages, of course, then we would never even need to go to the root server. Right, anyway, the top level domain server, so this stores the address information for top level domains, right, .com, .net, .org, etc. So if you've got okay. So again, if you've got a .com domain that you're trying to resolve, well, then it's going to say, right, okay, then you should go to this. For example, okay. So then it's going to sort of point you to the correct authoritative name server. Okay. So I guess you can just read that right there. .com TLD doesn't actually know all the .com IPs. Again, it simply knows which server to ask. Yeah, and I guess, well, the root server as well, right, doesn't list all the domains, it just has a list of all the top level domain servers. Okay, right, so then if we look at the authoritative name server, right, that's going to be this one here. Right, that's responsible for knowing everything about the domain, right, including the IP address. So yeah, that's going to have the DNS record. So again, just to recap, well, first it's going to check on the PC, right, the browser on OS. If they don't know it, well, then it's going to go to the router, right? Okay. So, okay, when we say the router, I mean basically what, just the local DNS server. Right, then if that doesn't know it, well, then it's going to go to, well, the ISP's resolver, right, the ISP's DNS server. Right, then it's going to go, well, root server TLD, and yeah, finally, well, the authoritative name server. Alright, and I think, yeah, maybe, yeah, okay, alright. So when the authoritative name server sends the IP back, right, to the resolver, then each of the previous stages was, yeah, okay, alright, so let's just draw that. So this is then going to send the result back. So let's say it's going to say, I don't know, yeah, google.com. Right, so google.com has the IP, yeah, 1234. Yeah, so 1234 like that. Right, so then what's going to happen? Well, here then the ISP's resolver, okay, well, that's going to store that IP address. Okay, so not really the IP address. It's going to store the entire record. So it's going to say, right, google.com has the IP address 1234. Right, likewise, of course, well, that's going to get sent back to the computer, you know, since, well, the computer needs to know, right, in order to know, you know, kind of, well, yeah, which web server to send it to, right, when it's, you know, making the request for yahoo.com. Right, so then we say, well, that's also going to get stored in the router's DNS server. Right, this will also get stored temporarily as well, yeah, in the browser, or yeah, well, in the, you know, browser's DNS server. And actually all of these are going to be temporary, like they're not going to be stored permanently. And again, well, that's for security reasons. It's also, for example, well, let's say if a server changes IP address, like if, well, yeah, okay. So let's say you have a website and, you know, you change server. Well, if the IP address was permanently stored, you know, people would always be going to the old IP address by mistake. Yeah, that's why, yeah, okay. So that's why you don't want it to be permanently stored. Yeah, so we can say, yeah, okay, alright, okay, so this process of kind of storing it in memory, well, that's called caching, right, yeah, temporarily saving it, right, therefore it won't have to repeat the process again. So if instead we try to go, alright, yeah, okay, so I think actually we weren't really asking for Google, right, I think it was actually yahoo.com in the example. So let's say if, I don't know, 5 minutes later we also tried to go to yahoo.com, well, maybe this is still going to be in the browser, you know, depending on how long it stores it. Right, yeah, okay, so if it is, well, then of course it just knows it already. If it's not in the browser, well, then it's going to go to the router. I guess here we actually haven't labeled the router on this, yeah, in this video. Of course, yeah, okay, so if it's still in the router's cache, well, of course that can get it, right, yeah, okay, so if it's not in the router's cache, well, then it's going to go to the resolver, of course, yeah, if that knows it's going to send it back, yeah, just etc. Alright, so yeah, hopefully that makes sense, right, how that works. Okay, let's just recap then. So DNS, well, it's going to be a hierarchical distributed database, and hierarchical because, well, as we can see here, well, we just got different levels. So for example, well, this DNS root zone, right, I guess, well, that's the root server. As we can see, well, the root server, and in fact, yeah, where is the thing? Okay, yeah, right, yeah, so here we go. Right, okay, so the root server, well, basically that's going to know all of the top level domain servers to ask. For example, let's say for a .com, you know, top level domain, right? Or yeah, .education top level domain. Right, okay, those top level domain servers, well, they're then going to know which authoritative name server to ask. Yeah, you know, based on the domain. And I guess you can see here, well, they're saying what the second level. So I guess, right, this is going to be the domain, right? Well, then here we've also got, right, subdomains as well. And when they say distributed, that's because what, right, yeah, okay. So what I think for the root servers, they said there was 13, yeah, 13 copies of those root servers. And yeah, okay, alright, okay, and also, well, the top level domain servers, right, it's going to be many of those, right, authoritative name servers, many of those. And probably you can think of some advantages of, well, yeah, okay, alright, okay, so try to think of some advantages of, you know, it being distributed. Well, one is going to be a backup, right? If one of the server fails, you know, you've got, well, a sort of backup, right? Well, yeah, I guess 12 more copies. It's also going to be good in terms of security. Like, let's say if one of the servers gets hacked, well, then you don't have, you know, just one source of truth. Because if you only have one server and, you know, that got hacked, well, then I guess, yeah, all the DNS records in the entire world, right, they're all just going to get, yeah, obviously, yeah, all, you know, messed up. Alright, and another one where it's going to be fast, because if you're in, let's say, whatever country, well, you don't want to be sending a DNS request, you know, to, I guess, someone on the other side of the world. Yeah, so it makes sense to have them, you know, close to where people are located. Alright, so actually, yeah, this actually says that root servers are replicated, right, for, well, backup and to provide, well, local or low latency access, right, to users in different part of the world. Right, so they're also divided into non-overlapping zones, right, so each zone has a primary server and secondary server. So I guess what primary, well, the main, obviously secondary, yeah, just backup. Alright, and there's, well, more than 250 generic or national top-level domains. Again, yeah, .com, right, obviously, yeah, etc. Okay, so yeah, I think this image we've seen before. So he said, well, left was the school Wi-Fi and right was going to be the office Wi-Fi. Alright, and I guess we can just see that here. Now, if we look at these DNS servers, now actually these are not the real DNS servers. I've actually changed these, you know, just for privacy reasons. However, if you actually look at the left one, well, since this is the school-wide Wi-Fi, this is actually directly connecting to the ISP. So these DNS servers here, okay, okay. So these DNS servers here, well, these would actually be my ISP's DNS servers. Yeah, and well, yeah, of course, right, okay. So if we try this one, well, of course, here we're not going to see any information on, you know, say ipinfo.io, since if we think, well, this is just, you know, a local. Now, if we think, well, if it's a local DNS server, well, then that's going to be our router. And if we look here, well, we see here 192.168.1, right, the subnet mask, well, 255.255.255, right, 0. So therefore, right, okay, so these first 24 bits are going to be the network. Right, therefore, if we look at this one, well, this is going to be on the same network, right, therefore, this is going to be our router. Right, when it's this one, so when it's 2, now this is a different network. Yeah, okay, so I would imagine this is going to be some, like, school-wide router. Yeah, I'm not entirely sure what that's going to be. But if we look at this one, well, this is definitely going to be our router, because yeah, if we see here, well, this is also the same as, well, yeah, the gateway, right, the DHCP server as well. Yeah, okay, all right, and then if we try for, I guess, well, the primary or secondary DNS servers here, again, you know, yeah, okay. So again, all right, okay. So these, yeah, so these should be my ISP's DNS servers. You can also just give them a kind of custom DNS server. Which you can see here. Now, well, yeah, okay, this, right, so, well, 1111, right, that's going to be Cloudflare's DNS server. I think Google, well, they have, what is it, yeah, 8888. I think maybe they have another one, is it maybe 88, maybe 44. Yeah, I think possibly both of those would be Google's DNS servers. So again, so you could choose just to use your ISP's DNS servers, right? You could also choose, yeah, some, you know, kind of third-party DNS servers like these. Yeah, and again, yeah, all right, okay, so I think that's just what I said. Yeah, the school network is, well, connected, you know, directly to the ISP's, yeah, DNS servers. All right, so let's actually see this in Wireshark then. And Wireshark, I think they would call that, what, like a packet tracer or, well, packet sniffer. Yeah, that's the type of program. Alright, so let's go to a random site I've never been to before, and also a random site that presumably no one else, you know, in the location has also been to. So something like, yeah, hello.io, right, some completely random website. Right, now, if we look at the packets then, since we've never been to this site, then, well, the IP or the DNS record isn't cached, right, in our browser or in our operating system. So this we can actually see. Now, this here, well, this is going to be my device. Right, this one here, well, I think this was the primary DNS server. Right, this one here is, well, the, yeah, I guess, well, the secondary DNS server. And of course, well, this one, right, yeah, this one, 1.1, okay, yeah, so this one was going to be our router, right, yeah, so if you remember that. Okay, so we said, yeah, DNS query sent from RPC, right, to our router's DNS servers. Well, yeah, okay, well, okay. Right, okay, so one of these is going to be our router. I guess, yeah, one of these is probably, well, yeah, okay, okay, so one of them is probably like the school router. Yeah, one is, you know, the actual office router. Right, and then, well, finally we can see the IP address 178, right, etc. was returned. And that we can see here, so it's saying, well, hello, right, has, you know, this IP address. Yeah, that's the, you know, DNS. Alright, and when it says 84, now I'm pretty sure, yeah, that's going to be in bytes. So it's saying, well, this response is 84 bytes. And as you can see here, well, obviously, yeah, the protocol DNS. And if we look here, well, this is going to be the packet number. Yeah, where is that? Yeah, packet number. Now, the reason the packet numbers are high, That's because, well, okay. So the reason the packet numbers are high is because actually this is capturing all the traffic. So not only this request, but I don't know, maybe I'm like using Discord simultaneously. So of course, there's other data, or maybe I'm watching a YouTube video at the same time. Sort of listening to music. Right, okay, so let's just recap then the DNS lookup stages. Right, first it's going to check the browser, the OS, the cache. Right, okay, then it's going to look the router's DNS server, right, then the ISP's DNS server, right, also called the resolver. Finally, then it's going to go to the root server, right, top level domain or authoritative name server. So if we look at this table, then was it possible that this DNS record was resolved in stage 1, right, i.e. browser OS? So I'd say pause the video, have a think about that. Okay, so hopefully you can realize no, because actually you can see our PC is sending a DNS request to the DNS request to the router, right, stage 2, right. Therefore, we know it wasn't resolved in stage 1, and the reason we say that again because if we look here, this is our device, right, and we see our device is then sending let's say to the school router and also the office router. So that means that obviously we're here, okay. So stage 1, of course, we couldn't resolve it. Alright, so again, I guess I've just put those 4 stages there. Right, so with Wireshark, we can only see the packets leaving and entering our computer. We can't actually see what happens to them, when they get to the router. And also, of course, what happens to them, once they leave the network. So we actually don't know if stages 3 or 4 had to be tried. Right, however, we can actually infer what stage was reached from the data, though. And again, I'll say pause the video. Right, have a look at these 4 packets and see if you can figure out any way of determining, what stage it probably had to go to. So, right, okay, so probably we can look at the time. Now, the times are in seconds, and I guess you can say, in total it took about 0.5 seconds. Obviously, from here, 0.18 until, 0.69. Or I guess actually, so this one, where's the thing? Right, so I guess, right, okay, so I think this one and this one are related, right, that's from the same request, and obviously, this one and this one are going to be related, same request, but still, I think overall it was about, let's say, 0.55 seconds. Now, if the router knew, then it's going to resolve that much quicker, certainly less than 5 milliseconds. Likewise, the ISP, since the ISP is actually in the same city, at least according to the online IP info site, then that's also going to be much quicker, right? Probably 20 to 40 milliseconds. Right, the fact it took 500 milliseconds, that suggests the relatively long process of stage 4, right, was going to be required. Obviously we're just going these various stages. Alright, so because of that, I guess that's why caching is important. Now let's think what's going to happen then if Wireshark, so what's going to be the output of Wireshark if again I go to hello.io within 1 minute. So if we look, actually it's just empty, and try to think about why it's going to be empty. Now, of course, the reason it's empty, since the browser has stored that DNS record, the domain name mapping to the IP address, right, in its cache, then the request therefore never had to leave the computer. Alright, and if you think again, the advantage of that is going to be faster, it's going to reduce load on the DNS server. Alright, so I think this we said, right, what's the benefit of caching? Basically what increases speed for the user, right, reduces load on the DNS servers. And as mentioned, caching occurs at all stages, right, so we're in the browser, right, the OS, the router, the ISP, authoritative name servers. Okay, alright, so I think that's also true. Alright, so let's say once the browser knows a DNS record, then do you think it stores it forever, right? Why or why not? And this one we've already mentioned, so hopefully people can remember. Right, so actually no, it's not going to store it forever, and by default I think it's only a short time, 1 minute. I think my testing on Chrome, it seemed to be about 1 minute, right? Maybe other browsers, might have different behavior. Right, so this is because, a website's IP or DNS policy could change, right? E.g., if they change server, if they change some configuration. Therefore, okay. So therefore, we don't want to store the DNS record forever because, okay. So in this case, then the DNS record will become invalid, right? If, for example, the website's IP is changed. Right, also for security reasons, let's say a website could be taken down, right, and a malicious site could be, now at that IP. So you wouldn't want to, for example, navigate to that IP address thinking it was one website, but it actually, turns out to be a different website now. Right, also, well, DNS spoofing or DNS hijacking. So if someone, let's say, modifies the DNS records to sort of navigate you to a different, okay, so if someone modifies the DNS record, basically to send your computer to a different IP address. And I guess also there's kind of a practical limit of storage size. So storing every DNS record for, I think now there's like, okay. So I think in total there's like more than 2 or 3 billion websites. Maybe more than that. So surprisingly, like there's almost as many websites as people. Like maybe like half. So of course, okay. So that's going to take a lot of space. If we just store them forever. Alright, so this is actually a bit more difficult now. Right, so we can't easily modify the browser's cache, right? But I guess we can, fairly easily, fairly easily edit something called the host file. Right, this is located at the following location. So I guess Windows, right, it's in there, right? Windows System 32, right? Well, Linux, Macs, etc, right? /host. Right, then you can then add custom DNS records easily. So the format is going to be like this, where first we're just going to say the IP address, right? Then we're going to say the domain name. Even though in some ways you might think it's kind of opposite, because, well, actually what we're asking for is we're kind of saying, well, what's the IP address of, well, in this case, Baidu.com, right? So, okay, so this one is going to be the question, and then, well, of course, the IP address, right, that's going to be the answer. So now I guess if you can see that, okay, so what I've done then, actually, this Baidu.com, well, this is actually the IP address for, well, QQ.com. Okay, so QQ, if people are not familiar with, basically just a messaging app, right, kind of similar to WhatsApp. Baidu, well, basically a search engine, right, similar to Google. So now, of course, I've got it where, okay, so when someone goes to Baidu.com, right, it's actually going to send them to QQ instead. Right, so using the ping command, I guess, just ping here. Right, then when we type Baidu.com, right, it's actually going to the QQ servers. Right, unfortunately, actually in modern web browsers, they seem to ignore non-local IP addresses in the host file. And I guess that's for security reasons, preventing people from, doing, DNS spoofing, right, DNS hijacking. Because otherwise, let's say you have, I don't know, some, malware. Now, the malware could just go in, so obviously, okay. So the malware could go in, add a load of custom DNS records. And then whenever you went to, Google, YouTube, well, then you go to the fake version. They could also use, okay. So they could then use that as a farming attack. Stealing your credentials. When you try to log in. So okay. So I don't know, like maybe there is a way if you sort of go into like Google Chrome settings. However, even sort of turning on various settings that apparently it should have worked. It seems on new versions where I actually couldn't get this to work. Although I do remember doing this sort of 10-15 years ago, and actually, this was pretty easy. If you just typed in, well, obviously, okay. So if you typed in a record like this, you could get it where you'd have, well, let's say, okay, so you'd go to Facebook, but, it would go to Google instead. And I think this we mentioned, right, it's just a security, kind of protection. However, if we want to do it for local IP addresses, well, that's going to be fine. Now, if you remember, okay, so we said, well, private IP address, like, 192, 168, also, 10, that was also going to be a private IP range. Right, when we say a local IP address, well, in this case, local just means, on our computer. So an IP address starting, 127, right, okay, so that's going to be just on our computer. So in this case, if we do it now, so we're saying, Baidu.com, right, instead, this is just going to go to this local IP address. And I guess what I've done, I must have set up a web server, probably just using XAMPP on Windows. So I guess, Apache, Apache, MySQL, right, PHP, and Perl. Alright, so probably just using XAMPP. I've just set up this website, and of course, right, okay. So now when they go to Baidu.com, well, now you see it's just going to give them this fake website. Okay, right, I think that's what it says. Right, so this then is an example of, DNS hijacking. Of course, this could be used more maliciously, right, e.g. creating a clone of the homepage, right, and then stealing their username and password, right, when they try to log in. And I guess, for financial websites, it's kind of even more of an issue, right, stealing bank details, credit card numbers, right, etc. Alright, so this one, I mean, these are just kind of extension tasks. Now, I would say this one, I mean, people should definitely do. So if you're on Windows, well, run ipconfig/all. And notice here, right, there's actually a space, right? If you don't have the space, it's not going to work. And this again, well, this is just going to show you all of your IP address, well, MAC address, DNS, right, DHCP, yeah, just all of these details, right? Try to look at it, try to understand it, because actually now you should be able to understand, 90% of it, right? Yeah, based on Unit 2. Right, so this is going to be a little bit more advanced. There's software, yeah, okay, right, okay. So this is, well, Cisco. Right, Cisco is in well, the company, right, CISCO. So Cisco, they have this software called Packet Tracer. And basically that's, yeah, right, okay, so that's software that allows you to kind of simulate networks. So what you can do, well, you can like drag and drop different computers, yeah, you can drag and drop routers, you can sort of give them, an IP address, right, give them a subnet mask, etc. So I would say, yeah, right, yeah, okay. So if anyone is like super keen and they sort of want to learn more about an extension task, well, then you can download Packet Tracer, right? Try and actually, sort of create two LANs, right? Connect them together, get it so that the computers can, successfully send packets between them, yeah, even across, different networks. All right, this you can also do. So if you're in a classroom, I guess, well, you can, yeah, ping other students' computers. So first you'd want to find out that IP address. And again, you can find out that IP address, okay, by running this, right? Yeah, then try to ping them, right? See if you can get a response from their computer. Right, and also I'd say go into the settings, right? Try changing, well, yeah, right, okay. So try kind of switching from, well, probably a static to a dynamic IP address. Well, yeah, right, okay. So actually, right, okay. So a dynamic IP address is probably going to be the default, yeah, if you're just on a router. So yeah, I would say, try going from a, well, dynamic to a static, yeah, try and set it up, yeah, make sure you can still connect to the internet. Alright, so some questions then. So for the following situations, what stage of the DNS hierarchy? Yeah, the name will most likely, yeah, right, okay, so, right, okay, probably what the domain name, right, will most likely be able to be resolved. So the first one, right, a website you haven't visited recently, but a colleague on the same network has. Right, then what a website, well, you nor people in your region have visited. Right, then clicking on a link on a web page that you just loaded. And right, finally, a website that you haven't visited, but many people in your region do. So if we think about what the different stages, well, one, what browser OS, right, then there's what the, yeah, right, yeah, okay, all right, okay, so what browser OS, right, then, well, the router, right, yeah, the router's DNS server. All right, then the ISP's DNS server, and then, well, finally the global. So, yeah, right, yeah, okay. Alright, so let's see what the global root server, right, then the TLD, yeah, top level domain server, right, finally, well, the authoritative name server. So I think this one is probably the easiest one if we think here. So if this is a website that you just visited, well, hopefully people remember, okay, this is going to be stored in the browser. So yeah, this one here, I guess we can say, right, browser, yeah, that's probably all we need to check. Right, let's say maybe, yeah, let's try this one. So a website that you haven't visited, but many people in your region do. Well, in this case, I mean, right, yeah, okay. So your browser, of course, is not going to know, right, since you haven't visited. Right, likewise, well, your, yeah, right, yeah, okay. So your router is also not going to know this DNS record, well, again, since you've not visited. However, since many people in your region have visited, well, then the ISP's DNS server is going to know. So yeah, this one, let's see what the ISP, yeah, yeah, okay. All right, so you probably say, well, the ISP's DNS server, or yeah, the ISP's, DNS resolver. All right, let's try this one. So a website, well, you, right, nor, yeah, right, okay, right, okay, all right, let's say maybe don't. All right, so a website, well, you don't, right, yeah, nor people in your region visit. So if no one visits, well, not even the ISP is going to know this, right, therefore it's going to have to the global. So let's see what, yeah, the global, well, I guess, yeah, global, sorry, / root servers. Right then, well, finally a website, and yeah, I guess we've done these in the reverse order, really. Right, a website you haven't visited recently, but a colleague on the same network has. So, of course, well, here it's not going to be in your browser, but since someone on the same network has, well, then your router should know this. So I guess, yeah, here we're going to see what the router's DNS server. So let's say, yeah, okay, that's going to be router, I guess, well, for, yeah, authoritative name server, right, global, right, then browser, and, well, yeah, the ISP's DNS server or resolver. Alright, so let's just end with some more questions, right? So why was IPv6 created and how many addresses can it represent? Now, as always, pause the video, have a think, right, and yeah, I guess, well, resume the video and yeah, see the answer. Right, so I guess primarily it was created to address the issue of there being too few IPv4 addresses. Hopefully people remember what that's, 2 to the power 32. 32, right, and that's approximately 4.3 billion. But as we remember, there's 8 billion people, right? Most people have more than one device. Right, IPv6 does also have a few more advantages. I think really they probably wouldn't ask this in the exam, although yeah, maybe they, I don't know, so like maybe it is possible. Right, so IPv6 also has the advantage, right, more efficient routing, right, also better security, and simpler network configuration, right, since DHCP servers are not required. Because if, right, okay, I guess you can also say the subnet mask is also included in the IPv6 address. Right, therefore that's also maybe a little bit simpler. You don't need to send, two separate things. Right, then in terms of how many, so 2 to the power 128 IPv6 addresses, right, that's 340 undecillion, right, which is, this number here. Alright, then let's think, what's a dual IPv6 address, and also why were they created? Alright, so if you pause the video, so an IPv6 address that also contains an IPv4 address, right, that's the definition of a dual address. Right, so that's going to be for backwards compatibility. So if hardware doesn't support IPv6, let's say it's old hardware, right, then it can use the IPv4 address instead. Whereas, of course, if it does support IPv6, then, okay, so then it may as well use IPv6, for the reasons here, right, I mean, more efficient routing, better security, I guess simpler network configuration. Right, okay, then we want to state whether the following IPv6 addresses are valid, and give reasons if they're invalid. So yeah, these are common kind of exam questions. Alright, so is this, okay. So let's just show all of them first, right, again, so pause the video, have a think, and then resume the video. Alright, so if you've if you had to think, let's just go through these. I'm going to look at the first one. So here, so here they all seem to be valid hex characters. Let's also count the groups. So group 1, right, 2, 3, 4. Okay, so here there seem to be 8 groups. Alright, so I think this one seems valid because if we think, here they're also all using the colon as well. That's valid. Right, then if we look at the second one, so I think the colon seem valid. Obviously, while leading zeros are being omitted, that's fine. Let's count how many groups. So that's going to be 4 groups. Right, that's another 4 groups. Right, so here there's going to be 9 groups. Right, therefore it's invalid. Right, if we look at the next one. Now the next one, I mean, maybe it looks super weird, but if you think about that carefully, this actually just means all zeros. So yeah, this should actually be valid. Right, then if we look at the next one. Okay, so maybe you can realize, here there's a problem that we've got 2 groups of zeros. So yeah, remember we can't have that because then how do we know if okay. So how do we know if there's 1 group of zeros here, 4 group of zeros here, or maybe I don't know 2 here, 3 here. It's kind of ambiguous. Alright, then if we look at the final one, so the final one, this also seems valid because I guess this is going to be the IPv6 part, all zeros, and then the IPv4 part, sort of dual address. Okay. So this seems to be a valid IPv4 address. Okay, then just a few more. So this one again, pause the video, have a go. I guess all of these 3. Right. So if we look at the first one, I mean that seems right. Okay. So I've noticed here, right, this one actually has 5. So that's going to be invalid. 5 hex characters in the 4th group. Right. Then if we look at the next one, so right. Okay. So I think here we can see there's a problem. So here we've got the colon, right? Then we've got a full stop, right? And of course, right? Okay. So then we just got more hex characters. So we can say invalid because I guess the full stop is in the IPv6 portion, right? Then if we look at the final one, so I think final one, we just see a G here, right? Therefore that's going to be invalid. Okay. Then we want to ask, what is DNS and how are DNS requests resolved? Alright, so if you pause again, right, so DNS is a way of mapping a domain name, which they're easy for humans to remember, right, to an IP address, and IP address, they're right, so IP address is used for network routing. Right, the following stage will be checked to see if it knows the IP address for this domain. Right, if it does, then the answer will be returned, or I guess the IP address will be returned. Right, and the other stages don't need to be checked. And I think this one we've sort of seen many times, right? So first the browser, then the OS. Right, then the router's DNS server, right, then the ISP's DNS server or resolver, right, then the root server, the TLD, right, top level domain server, and finally the authoritative name server. Right then, I think the last question, so why are DNS records cached? And this one, well, that's going to be to reduce load on the DNS servers and also improve the DNS query response time, while effectively kind of reducing the latency. Yeah, okay. And that's also kind of helped by the fact that we have many DNS servers around the world, yeah, just so they're close to users. Okay, then just a summary of the whole chapter. So, right, there's going to be the client-server model and peer-to-peer model. Now, client-server, hopefully you remember, that's going to be where, well, right, okay, so we have a client, right, they're going to send a request to the server, right, the server is going to process that, right, then it's going to respond. Now, that's quite reliable. However, I guess it can be a little bit slow, right, because, well, basically you've just got, sort of one person you're downloading from, or one device you're downloading from. Right, so that's why peer-to-peer was developed. Well, yeah, right, okay, so that's one reason peer-to-peer was developed. I guess, well, another reason, it's also used to, let's say, share illegal files, right? So, yeah, harder to track, harder to, close down. So peer-to-peer, well, rather than just communicating with one device, right, there's going to be many devices, or, well, many peers, many nodes, and you can be kind of uploading and downloading different files, from different peers simultaneously. Right, then it's going to be, well, different topologies. So, for example, star topology. Yeah, does it mention any of the others? No. Right, so, well, star topology, bus. Right, there's going to be what the mesh, right, and also point to point. Now, when we say mesh, well, there's two types. So, well, full mesh and partial mesh. And right here they say the star topology is most commonly used for LANs, where you're going to have, well, one switch in the middle. Of course, all the devices just connected to that switch. Right then, well, transmission media, well, it's going to be copper, so, well, that's twisted pair coaxial cables. Fiber optic, of course, using light. Right then, wireless, well, radio, right, microwave, and infrared. I guess, well, satellites, right, right then, factors to consider when choosing a medium, well, it's going to be bandwidth, so kind of the rate of data, right, okay. So bandwidth is going to be the amount of data we can send per second, or, per unit time. Right, attenuation, that's going to be the rate at which the intensity of the signal decreases, right, over distance. Right, interference, I guess, when you have two signals, kind of just, affecting the wavelength of the other signal. Therefore corrupting the data. Right, and also, well, the need for repeaters. So the need for repeaters, that's going to be, I guess, inversely related to attenuation. So something that attenuates, right, all right. So not inversely related. Okay, it's going to be directly proportional. So something that attenuates more is going to need more repeaters, right? Something that attenuates less is going to need less repeaters. Right then, CSMA CD, right, carry sense multiplexers with collision detection. Right, that's used to detect collisions. Now that was used on the old bus networks. Kind of before we had full duplex. Now, if you remember how this works, basically it's going to check the wire, right, to check that there's no voltage. Now, if there is a voltage, it's going to have to wait because, okay. So if there is a voltage, well, that means someone is sending, right? If no one is sending, well, then it will try to send, right? If there's no collision, well, then I guess it's successful, right? It doesn't have to do anything, right? If there is a collision, so if it detects there's a collision, well, then it's going to send a jamming signal. Right, then I guess after the jamming signal, well then, both devices will stop sending. Right, they're then going to wait a random amount of time. Right, then they'll try and resend again. Now, the the reason they wait a random amount of time is because, if they waited the same amount of time, right, then they're going to send again, and there's going to be another collision. Whereas hopefully, if they both wait a different random amount of time, well then, one of them could start sending. Right, the other one is then going to detect that someone is sending, right, since it can measure a voltage, right, then it's going to wait until they finish, right, then they can send. Alright then, the internet, right, it's the largest internet network in existence, and I think they also say the internet, is just a big WAN, right, a big wide area network. Right, ISPs, internet service providers, they're going to provide access to the internet, so I guess, you pay, your monthly internet fee, right, to, connect. Right, internet infrastructure is supported by PSTNs and cell phone companies, right? PSTN, the public switch telephone network. So that's going to be using circuit switching, where traditionally you'd actually have an operator who's going to be, physically unplugging a wire and, plugging it into another port. I think now that's actually done digitally instead, but I guess the sort of concept is the same, where you're going to have an actual, dedicated connection, right, from the sender to the receiver. Right, that's in contrast with packet switching, where packet switching, there you're going to have shared infrastructure. So you can have many people, sending data on the same, let's say, fiber optic cables. yeah, many people sending data, you know, via the same routers. You can say, well, the data is going to be split up into individual packets, right? Yeah, okay. So it's going to be split into individual packets. The data can then travel, well, okay, okay. So let's say the packets can then travel different routes along the network. When they get to the receiver, well, the receiver then may have to reorder them, right, if they've arrived in the incorrect order. Also, if it's not received all of them, well, then it can, you know, ask for some of them to be resent. Yeah, kind of have the packets that haven't arrived. So those packets should be resent. Right, the World Wide Web, www, is a distributed application accessible on the internet. Yeah, I think that's a bit of a strange definition. Like, really, the World Wide Web, basically, it's just the collection of all the web pages. So I think the definition they given in the exam usually say what is the collection of all the web pages that are linked, or yeah, I guess connected via hyperlinks. And obviously, what hyperlinks just being what the sort of links you can click on. Right, so the current internet addressing scheme is IP version 4 or IP version 6 of future contender. Okay, so actually you can kind of go on, okay. So there's actually websites that will tell you, you know, sort of the percentage of people using IP version 6. I think now it's actually quite a significant amount. And to be honest, it also depends on countries. Like, I think there's some countries where like 90% are using IP version 6. Yeah, some countries where, you know, still like almost zero. Alright, then finally, well, DNS resolves a domain name to an IP address, again, well, just using the various stages as we've seen today. Alright guys, so hopefully all of this makes sense. I would say, well, if some of it doesn't, I mean, well, yeah, of course you can go back, watch a previous video, you know, just recap this right in the book. Yeah, use, you know, ChatGPT, right, yeah, whatever you're going to do. But as always then, hopefully this video is useful. Any questions, ask in the comments, and I'll see you again in the next video. And actually, just to say, well, the next video will probably just be a recap, right, a revision of all of Unit 2.